Now, we'll start asking the question, how do you get the derivative of the trig functions sine and cosine? Now, again, as usual, if you just want the punchline, it's this right here. The derivative of sine is cosine, the derivative of cosine is negative sine, and that's all you really need to know. But I will spend the rest of this video doing a proof of that fact. So, as a bit of preface, we're going to, once we're about halfway into the proof, I'm going to need the formula for the sine of a sum of angles. So I really need this right here. Now, there is an ancient Greek derivation of what this is by looking at circles and adding angles. But it is messy. It is not a fun proof, and it doesn't fit easily on a page like this. So and it's also kind of complicated. You can see it's a bit of a mess. I always get it confused with exactly what you do for the cosine run. I get these two confused often, and so I choose not to remember it. Instead, I know Euler's formula. Now, this is probably a bit scary looking formula, but it is really a thing of wonder. And later on in the calculus sequence, we'll actually see a justification for this equality. But at least for now, let's just kind of take it as fact. And if we do so, it'll allow us to get easy ways to figure out the sine and cosine angle sum formulas. So how do I do that? How do I exploit Euler's formula to get the sine and cosine formulas? Well, it makes just good sense that here I'm talking not about a single angle, but a sum of some two angles. So if I apply Euler's identity to that, I get exactly as you would expect, that right there. But also I can use what I know about exponentials, namely that I can distribute the I and split up the exponentials. You should be very familiar with the fact that these two multiplied together results in e to the sum of them. So, but now that I've split it up in this way here, applying Euler's formula to each one individually gets me this product. I distribute the multiplication, and then think about what happens if you group the real and the imaginary parts. I guess I should be commenting that this I is the imaginary number I, and so this has real part cosine alpha plus beta, and it is equal to this, which has real part cosine alpha cosine beta minus sine alpha sine beta. So that tells me the angle sum formula for cosine. And if I look at the imaginary part, I see sine alpha plus beta, so I'll be able to read off the sine angle sum formula by just factoring I from these terms and then looking at what's left over, right? I mean, just set this equal to this and cancel out the factor of I because they both have it, and you get that sine alpha plus beta is cosine alpha sine beta plus sine alpha cosine beta. And this is the one that I'm going to be needing. But so just, if you found it useful, I hope you did. I think it's really incredible that something like this can be so handy. This is not the only use of the formula. That is an extremely powerful formula. But this is one sort of nice, interesting little application of it. So anyway, let's now get into the derivative of sine. And I'm going to go using the definition. So here I state the definition of the derivative. I apply it to the sine function. Now, at this step, I use the sine angle sum formula on x and negative h, right? So alpha is x, beta is negative h. And so I get this. Now, the next thing to use is the fact that sine is an odd function. You should recall that from trig. And because it is an odd function, you can take that negative on the h and move it to the outside here. Oops. And so when I do that, that well, let's just sort of table that for now. So regard the negative as having been moved to the front of the cosine. And here, recall that cosine is an even function, which means that you can just drop the negative altogether. After having done that, right, moving the negative here outside, here dropping the negative, let's group together the two terms that have sine x in them. So that's this term here, which is sine x cos h, and over here, sine x. Or, keep in mind that you need to distribute the negative, so it's going to have a negative in between them, and then we factor out sine. So that explains why you've got sine x times this thing, is that it's the result of factoring out sine x minus sine x cos h. So after factorization, you get this. The remaining term, you're going to have a negative times a negative, which causes a positive, and the remaining part is cos x sine h. Now, at this point, we distribute the h to the two terms, and you have right here 1 over cos h, 1 minus cos h over h, which we proved was 0 in the section on limits. Over here, you have sine h over h, which is equal to 1. So the only thing that's left over is cosine x, and that is the derivative. So we could do the same process to figure out the derivative of cosine, but in fact, I'm not going to do it. I'm just going to assert and have exercises using the fact that cosine x has derivative negative sine x, and I will, in fact, later on prove something called the chain rule. And once you have the chain rule, you can just use this identity together with the chain rule and get the derivative. So I'm not going to give you the derivative of cosine. I'm not going to do the proof of it because it's actually easier if we first prove the chain rule, which we have to do anyway. So why not just do that?